Hi, my name is Chris Jones, and in this video we will be reviewing the three sorting algorithms that are tested on the AP Computer Science A exam. Those three algorithms are selection sort, insertion sort, and merge sort. To review those three algorithms, we will be sorting a list of blocks. I've got some blocks here. These all look very similar other than the fact that they have different letters on the top, but they actually weigh different amounts, different densities. I 3D printed these so they have different infill, and our goal here is going to be to sort them by weight. So my goal is that it's not very obvious by looking at them which one weighs the least and which one weighs the heaviest. Just like in Java, when we want to compare two objects, we will need to use a comparator. So in Java, we usually write a method that we call compare to that takes two objects and tells you which one comes before the other. In our simulation here, we will be using a scale. So I can place two objects on the scale and it'll tell me which one is heavier. So we will start by reviewing selection sort. That's our first algorithm. And I will use this sticky note to keep a tally of how many comparisons I have to do as I go through this sort. So selection sort starts by dividing the array into two logical arrays. The first one is the sorted portion of the array, and the second is the unsorted portion. At the beginning of selection sort, we say that the entire array is unsorted. So I'll line up my array over here on the unsorted side. The goal of selection sort is that we will slowly move more and more to the sorted side until we get to an entire sorted array. So to start off with, I will take my first two blocks and compare them to see which one is lighter. And I can see, it's a little bit tough to tell on my scale, that A is lighter than B. In Java, when we're doing comparisons, we're not actually removing things from the array, so I'm going to be careful to put things back in the array every step. And now I know that A was lighter than B, and so I will keep that one and move on, and I can compare that to the next one. I can see that C is quite a bit lighter than A. I like to think of this process as like a ping pong or table tennis tournament where the winner stays. So C is my new champion of light cubes, and so I'll keep that one. I'll put them back in the list to make it clear that we're not actually removing them from the list at this point. But I know that C is my lightest so far, so I'll compare that one to D, and I can see that C is quite a bit lighter than D. I will compare C to E. Oh, and I can see that E is lighter than C. So this is my new champion of lightest cubes. I don't need to go back and compare E to A, B, C, or D because I know that C was the lightest of those and E was lighter than C. So I can move forward with E as the lightest cube I've found so far. We'll place it back in the list just to make it clear. I'll compare E to F, and E is lighter than F. I'll compare E to G, and E is lighter than G. And I'll compare E to H, and E is lighter than H. Okay, so now I'm at the point where I have identified that E is the lightest cube in my list. And the way that selection sort moves E to the front of the list is through a swap. So I'm going to take E and the first item in the list, and I'm going to swap them. So E goes over here, and A goes over here. Now that I know that E is the lightest item in my entire array, and I've moved it to the front, I can slide my little marker to say that E is in the sorted portion of the array now, and the rest of my array is unsorted. Let's update our tally. To go through this process, I started with 8 cubes. I had to make 7 total comparisons to get to the point where I understood that E was the lightest. So I'm going to add 7 to my tally over here. 7. So now I can repeat the process, and I'll go a little bit faster this time. And the idea here now is that I have an unsorted array of size 7. That's everything other than E. And my goal is to find what is the lightest cube of this unsorted array. When I find that, I'll swap it with B, and I'll be able to move forward and repeat and repeat and repeat until I get to the end. So one thing to note at this point is our computer doesn't remember. We, as humans, remember that C was a pretty early champion. The computer doesn't remember. It thinks of this as a whole new problem. I've got a new unsorted array here of size 7, and I need to find the lightest cube here. So we'll go from the top, and we'll find the lightest cube in this unsorted array. So I've got B and C, and I'll compare them, and C is lighter than B. And I'll put them back. And C versus D, C is lighter than D. And I'll put these back. C and C is lighter than A. We've got C and F. Ooh, this one's a little bit tough to see. C appears to be lighter than F. We've got C and G, and C is lighter than G. We've got C and H, and oops, C and H, and C is lighter than H. Okay, so now I know that C is my next lightest cube in my list. Again, I'm going to swap with the cube at the front of my unsorted list, and now I can move my marker, and I now have a sorted list of size 2 and an unsorted array of size 6. That took me 6 comparisons, so I'm going to add 6 to my total here. Camera a little bit. And I'll repeat again, and once again, I'll go a little bit faster this time. So I'll compare B and D, and ooh, it's hard to tell. My scale is a little low precision here. So B was lighter than D once I gave it a little jiggle. I'll compare B and A. Always got to reset my scale to be balanced. And oh, A is lighter than B. Okay. And I've got A and F. F is lighter than A. So F is my new champion. I've got F and G. And it looks to me like F is a little bit lighter than G. And now I'll compare F and H. And F is lighter than H. Okay. F is the lightest of my subarray. And so I will swap it with the front of my unsorted subarray. And then I can shift my marker over a little bit. I now have an unsorted array of size 5. And that took me 5 comparisons. So I'll add a 5 to my tally. Okay, start again. I compare D and A is lighter. I compare A and B is lighter. I compare A and G is lighter. I compare G and H is lighter. Okay, G is the lightest of this subarray, and so I will swap it with the front of the subarray, and I will slide over. I now have a sorted array of size 4 and an unsorted array of size 4, and that took me 4 comparisons. I'm going to find the lightest of my unsorted subarray, so I'll compare A and B, and A is lighter. I will compare A and D, and A is lighter. I will compare A and H is lighter. So I know that H is the lightest of my unsorted subarray, so I'll swap it to the front of the unsorted subarray and then move over my marker. I now have an unsorted subarray of size 3, and that took me 3 comparisons. Now I've got to find the lightest of this unsorted subarray. I've got B and D, and B is lighter. I've got B and A is lighter, so A was my lightest. This time it only took me 2 comparisons. I'll swap it to the front of my unsorted subarray and do like that. And that took me 2 comparisons. I'm going to come back up here so it stays on the screen. And now I just have an unsorted subarray of size 2, so I'll compare these two. And B is lighter, and so I will swap it to the front of my unsorted subarray, move that over. That took me 1 comparison. And now my unsorted subarray is only size 1, so I don't need to do any comparisons. I can kind of skip over that last step. That took me 0 comparisons is a good way to think of that. So now I've got a fully sorted array. We see that E is the lightest all the way down to D is the heaviest. That's selection sort. Let's tally it up. This took me 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 plus 0. That is 15, 25, 27, 28. 28 was my total comparisons here. All right, we are going to move on to insertion sort. So I will reorganize my list back to my scrambled order. Same deal with insertion sort. It starts with a sorted and an unsorted array. And we're going to put everything over here on the unsorted array. Insertion sort is different. The goal of insertion sort, every step of the way, we're taking the very first item in the unsorted array and we're putting it into the sorted array. So we're trying to figure out where it goes into the sorted array. So the very first step is easy. I have my first item in my unsorted array and there's nothing in my sorted array. So I'll just go ahead and move it over. So that one's easy. And let me get my new sticky note to keep track of my steps for insertion sort. The very first iteration of insertion sort, when we moved the first cube into the sorted array, that took me 0 comparisons. Didn't have to use my scale at all for that step. Okay, so the next step is we're going to take B. B is what we want to insert into the sorted array, and we want to see where it goes in our sorted array. So each step of the way here, I'm going to start at the left side of our sorted array, and I'm going to stop when I find something that is heavier than B. So here's how this works. I'm going to compare A and B, and I can see that B is heavier than A, and so I know that it goes to the right of A. So that took me one comparison. My sorted list is now size 2. My next goal is to insert C into my sorted array. And so I'm going to start all the way at the left. I'll compare C to A. I know that A is heavier than C, and so I don't need to compare C to B at all. I can say that C goes to the front of this array. So that took me one comparison. Okay, my unsorted array now is of size 5. D is what I want to insert into my sorted array. Same deal, I'm going to start at the front and stop when I find something that's heavier than D. So I'll start comparing by D to C. D is heavier than C. I'll compare D to A. D is heavier than A, and I will compare D to B. And it's hard to tell, but D is heavier than B. So in this case, I have done 3 comparisons, and I know that D is the heaviest of my sorted array. So that took me 3 comparisons. Okay, my unsorted array is of size 4 here. I want to insert E into this sorted array. So I'll start at the front. Is E heavier than C? C is heavier than E. So I already know that E is going to be the lightest in my sorted array. So it can go right to the front. I don't need to compare to any of these because I know these are all heavier than C, and C was heavier than E. So that took me 1 comparison. Okay, now I want to insert F. Let's start here and compare E and F. I know that E is lighter than F. I'm looking for something that's heavier than F, so I'll move on. Is C heavier than F? It's hard to tell, but C is lighter than F. Let's compare A to F. Oh, A is heavier than F. Okay, so I know that F goes right here in my sorted array. That took me 1, 2, 3 comparisons to get there. All right, and I'm going to slide this over a little bit. My new goal is to insert G into my sorted array. I'll start at the front. Is G heavier than E? It is. Okay, I'm looking for something that's heavier than G. Is C heavier than G? Nope. Is F heavier than G? It's a little tough to tell. Nope, F is not heavier than G. Is A heavier than G? Oh, A is heavier than G. Okay, so G gets inserted here into my sorted array, and that took me 4 comparisons. And now I've only got 1 left to insert into my sorted array, and I will start all the way at the left. So I'm looking for something that is heavier than H. E is not heavier than H. Is C heavier than H? Nope. Is F heavier than H? Nope. Is G heavier than H? It's close, but nope. Is A heavier than H? Yes, A is heavier than H. So I know that H goes in front of A. So that one took me 1, 2, 3, 4, 5 comparisons. And we have a fully sorted array. So here's my completely sorted array. I got the same answer as I did before, which is good. Let's tally up our total. This took me 5, 10, 14, 18. 18 comparisons to complete insertion sort. So one thing I didn't do a good job of highlighting is the actual insertion process for insertion sort. So when I just now was trying to insert H into this array, I figured out that it needed to go at this spot in the array. Different implementations of this algorithm will work slightly differently, but the important part that we need to think about is that we have to clear a space for inserting H into the array. So some of the work insertion sort involves pulling H out, moving D to that spot, moving B to that spot, moving A to that spot, and then we can insert H. So I didn't do a great job of explaining that. I'm focusing on the comparisons here, but you'll want to look at some implementations of insertion sort and see how they handle that. Okay, we've done 2 of our 3 sorts. Merge sort is the weirdest. Merge sort does not involve dividing our list into sorted and unsorted, so I'm going to remove this part. And let me grab my merge sort sticky note so we can keep track of our comparisons for this one. And I will reset back to our list here. Okay, merge sort is a recursive algorithm. And the way that the recursive algorithm works is it starts by saying, let's divide our array into two parts. And we will merge sort the first part, we will merge sort the second part, and then once these two are sorted, we'll be able to merge them together. Let's quickly review what merging looks like. So if I have two lists and I want to merge them together, I'm only ever looking at the very first part of the list, and I'm taking whatever is lightest. I'm not going to go through the whole process for this part right now. But the idea is if I compare these two and I find out that A is lighter, then I would pull that down. And then I would compare these two and figure out which one is lighter. And over time, I would slowly pull them together and merge them into one list. I like to think of this like traffic merging on the highway, right? So we are going to, for now, discard the second side of the list. Our goal here was to merge sort the first half and then merge sort the second half. And then once these two are sorted, we can merge them together. So I'm going to discard this side for a minute. Now I have this list, and my goal is to merge sort this list. The same deal here. I'm going to divide this into two logical arrays. I'm going to merge sort the first half and then merge sort the second half, and then I'll be able to merge them together. So I'm going to discard this side for a second. I can take this and divide it into two logical arrays. I'll merge sort this side and merge sort this side, and then I can merge them together. Now these arrays are both of size 1. This is the base case for the recursive call in the merge sort algorithm. At this point, I know that these can both be considered to be sorted subarrays. So my only goal here now is to merge sort them together, to merge them together. Merging two arrays of size 1 is really easy. I'll just compare them and I'll see which one is lighter. And this one's always a little bit tough. A is lighter than B, so A is going to go in front of B. And I consider this now a sorted array of size 2. So I will say that that took me one comparison so far. Okay, now I know that this subarray is sorted, and so I want to go back to this subarray that I need to eventually merge it into. I can now sort this one. Remember, I divide it in half and merge sort the two independently. These are both subarrays of size 1, and so I consider them to be sorted, and my goal now is to merge these together. I'll compare them and see which one is heavier. C is clearly lighter, and so in my sorted subarray, C comes before D. I now have two subarrays of size 2 that are independently sorted, and I need to merge them together. Oh wait, forgot to tally that. Okay. So to merge them together, I look at the lighter, the first cube in each subarray, and I'll compare these. And C is lighter than A, so I know that in my final array, C needs to go before A. I'm going to pull this out. This is a little bit of a simplification, but I'm going to slowly build my merged subarray. So now I have A is at the front of this list and D is at the front of this list. I'll compare these and see which one is lighter. A is lighter than D, so that's the next entry into my sorted array. Of my original list, I now have B is the front of this one and D is the front of this one. So I'll compare these ones. And it's a little tough to tell, but B is lighter than D. So I'll insert that, and then I've got the one left. This comparison and merging these two subarrays, first I had to compare the first two elements, and then I had two left, and then I had one more. So I think this took me 3 comparisons. Okay, this is an entirely sorted subarray of size 4, and so I'm going to set this aside for a minute and return to this subarray of size 4 that I started with. In order to, my goal here is to do the same process for this one. So I'll go a little bit faster. I'll divide this in half, and I'll discard this half for a second. I'll divide this in half. These are now independently sorted subarrays of size 1, and I need to merge them together. So I'll see which one is lighter. E is lighter than F, and so here is my sorted subarray of size 2. Let's bring back this one, separate them. These are now sorted subarrays of size 1, and compare them. And G is lighter than H, and so this is my sorted subarray of size 2. I now have 2 sorted subarrays of size 2. Oh wait, let me mark that took me 2 comparisons, 1 and 1. Okay, now I need to merge these together. Same process, I'll start with the first cube from each sorted subarray and compare these. E is lighter than G, and so E gets pulled down into my sorted array. I've got F and G, and I need to compare these to figure out which one is lighter. F is lighter than G, so that gets pulled down. And now I have my entire subarray GH, and I know that GH is lighter than E and F, and I already know that G is lighter than H because this is a sorted subarray, so I can just pull the whole thing down. So this time it only took me 2 comparisons. Okay, remember at the very beginning, we said that we took our subarray, we divided it into 2 sorted subarrays, and then now that we have these sorted, we can merge them together. So these are both entirely sorted now. We can merge them together to get to our final array. So same deal, I'll start at the top of each, the front of each list, and I'll compare these two. I can see that E is lighter than C, so this is the one that gets pulled down. E is going to be the lightest cube overall. I compare C and F, and C is lighter than F, so this gets pulled down. Now I can compare F and A, and F is lighter than A, so this gets pulled down. Now I can compare A and G is lighter than A, so it gets pulled down. I'll compare A and H is lighter than A, so this can get pulled down. Now I have my entire original subarray here can get pulled down because there's nothing left from my other array to compare it to. So this process took me 1, 2, 3, 4, 5 comparisons. So it's out of 5. And I'm done. This is my entirely sorted array of size 8. And let's add up our total. This took us 10, 11, 12, 13, 14 comparisons. So we've now gone through merge sort, selection sort, and insertion sort, and we can compare them all to each other. Selection sort was the first one we did. It took us 28 comparisons. Then we did insertion sort, which took us 18 comparisons, and then we did merge sort, which took us 14 comparisons. So to summarize, selection sort was all about going through our unsorted section of our array and finding the lightest cube and then swapping it into our sorted portion of our array. Insertion sort was all about adding one thing from our unsorted array to the sorted array at a time. And then merge sort used that recursive process. We divide it in half, we sort both of the halves, and then we merge them together. You'll get different performance for these based on the different values in your array. In general, though, this is pretty consistent. We'll see that selection sort is usually the most expensive of these, so it takes the most comparisons. Insertion sort will be more performant if your initial array is very close to sorted. So my initial array was already pretty sorted, and so this is a pretty reasonable time for insertion sort. And then in general, merge sort is usually the fastest. It doesn't have to deal with all of those comparing every single cube to every other cube every time. So this is pretty consistent. I hope this has been a helpful review of these 3 algorithms: merge sort, insertion sort, and selection sort. And if you're watching this, good luck on your AP exam.